beforehand a little bit. You are still coming in. Okay.
So our class is finished.
Yes. The lab has just finished. Let me see. Okay, I need to open this one up. By the way, just to check with you, this is week 3, right? Week 3, this is 9, 8, 7, 6. Yeah, correct, 6. This is 6 of July. Now, just to remind you, we have maybe I just want to check with you. We have a holiday, public holiday on the, I think on the, according to my calendar, it's on the 20th of July this month. So that is, I think, it's a national holiday, I believe, right? So it's on a Tuesday, which is on the what? This is on the Tuesday, which is on odd week. So affects the let me check. Affects the tutorial, and it affects 2 tutorials. The REE Group 3 and the RMH Group 1. Right. So I give you a choice. Someone is still coming in. The choice is we have a replacement for these 2 tutorials. Now we'll find the time to invite you all to join the other, what I call replacement class. And again, this is because of the, what I call it, the government policy, MQA, says that you are not allowed to take any holidays. Basically, what it's saying, any holidays have to replace. So basically, what it's saying is that no holidays, right? So we have to follow up Menurut Perintah. So the first tutorial is on the morning, Group 3, REE 4, and then Group 1, RMH 4. This is from 12:30 to 1:30. So A, we replace it, means I have to find a time slot where you are free. Or B, I think easier one will be you join the other groups. This is a week one. This is week odd week. So yours is the first one. So you all can join the Thursday. REE 4 Group 1. That means that Group 3 join Group 1 on Thursday. Is that okay? I mean, I'm just not. I'm giving you the option. I think easier if you join them. Now for MH, I'm not sure of the timetable. MH looks like MH. There's only 2 groups. Because your group is smaller. Your class is smaller, so you don't have any tutorial on any odd weeks. So, I mean, it's always odd weeks. Put it this way. So that means that option is for you to join your other classmates on the following week, which is an even week. MH4 group join the Group 2. Or C, MH join the EE students for the tutorial. Right? So I give you, what is your so-called, what do you think? What is a better way to solve this problem? Because as I said, we have to replace the lectures, we replace everything. Lectures, tutorials, everything. So no holidays. That's how I look at it. What do you think? No preference?
Yeah.
Yes. Thursday will be morning. Samuel has the question.
Lecture.
Sorry, what is it?
So do you we replace 1 week only or multiple weeks?
No, because it's a tutorial 1 hour only.
Oh, okay. Sorry.
I think it's let me see. On the 20th is a holiday. What is it? So come and check for me. I think it's I think our Muharram, is it? Something like that. According to my calendar.
I think just list it down on the chat to see our options here.
Yeah.
Ah,
So
okay,
because
okay, wait,
you mentioned it a bit hard for us to
Okay,
see
okay,
what's going on.
understand. Wait, let me confirm first.
Hari Raya Haji.
Haji, is it? Holiday, right?
Yes.
Yeah, right, Haji, correct. On the 20th, so I just realized that. Okay, so maybe I can. No, I think Christopher. I think let me see. It's not 2021. But it's 20. It's on the 20th. Replace. Replace tutorial on different day. Okay. B. Join your classmates. EG, I think join on Thursday morning. C for RMH for join RMH on the following week. E RMH join the REE on another day, on another convenient day. Convenient day. There you go. We check, And Thursday, okay. It looks like I have only 1, 2, 3, 4, 5, right? So MH, if you join the REE, has to be morning, 8 to 9 on a Thursday. That same week, 22nd of July, right? If you don't want to join too early, you want to join back your own classmates, you can join on the following week. This is 22nd plus 7, right? So the 27th of July. Is that clear? So maybe okay. If your rest of you do not know yet, I can send you a quiz or a poll to the Google Classroom for you to fill up. But at this point in time, just because you see, if I want to replace on a different day, just for you, for each class separate, I mean, I will find the time slot, right? So I don't know your timetable, I need to check. So I just want to find out, at least for the time being, what is your general feeling? That you are very shy, don't want to join your classmates in the tutorial, so you want your own slot. Actually, that's an E. I'm not sure. I'm just suggesting. I don't get offended. Just is continue to have the tutorial on the day.
What day is it?
Tuesday.
Tuesday.
Because the holiday is on the Tuesday.
Yeah, I think put that as an option. I'm not sure how many people who are actually busy on the who are actually busy.
Unless you guys are So what's the general opinion? Any violent objections to any of this? Said no, I don't want to join the other group. I'm going to stick with replacement class. To have a general feeling.
I'm okay with majority vote, sir. But for Thursday, when, sir?
It's your what? Jing Yong, your EE or MH?
RMH.
The EE tutorial is on the morning 8 to 9. Do you have a class?
8 to 9. For next week, right, sir?
No. It's an odd week.
Oh, odd week. 8 to 9. Yes. We have a robotics class from 8 to 10 actually.
Okay. So it's how
because of replacement.
So see, what is it?
Change of time.
It's actually this is our
yeah.
cannot cannot work. Okay, get out already. So there's leave only A, B, C, E. Okay. So looks like this one cannot be solved so easily. So of course the easiest one is replacement, or B, continue the same class on the day. Unless some of you have go for something on the day. This is a holiday, so-called holiday. Okay, so something to think about. I'll come back to this later on. Okay. Meanwhile, let's start the lecture. Yeah, all right. Wait. Let's see. Jim Yong can join the other group, MH tutorial. MH tutorial will be the following week, which is even week. That's also easy. Means you don't have a class on that odd week, so the tutorial is a bit delayed. That will be easier, so you don't have to, come for extra class in that sense. Now, of course, if you join the other group, Jim Yong, is always alternating, even week you got the I don't know whatever group, group 1 or group 2, then the other week is the other group. So when the other group has a tutorial, are you guys free? Here's the question.
I think so, sir.
What is it?
Sir, you're talking about the replacement on Tuesday. Is it on odd even week?
Yeah, it's actually you join the other group, MH,
which
same
is
time slot.
Which is
even week.
Yes, I think no problem unless somebody else got plan already. But if no plan, if not nobody got plan, actually that time slot is okay one, because we don't have any other class during that time for even week. I mean.
So there's one option. Now then come to anyway, I think I will not dwell on this anymore, because I know it looks like we cannot settle it this morning. But just want to get a feeling of it. So of course this one is a very very strange. So looks like we cannot have holidays. Once you have holidays for replace, so back to normal, isn't it? It's no holidays. Okay.
Now it's holiday
No holidays, like still got to replace one. It's like if you're working holiday, but you still come back to work on another day, replace it. So effectively, I think applies to all your lectures and your tutorials on the day. So you have lectures on the day, the whole day has to be replaced. So something to think about. Okay, before I start the lecture, are there any questions from the previous topic on the search? I think okay. No questions. So let's continue. So today we continue and go a little bit deeper into the search. So now we talk about this topic on heuristic search. So this is another type of search, and then you see what it is. Assignment. I think assignment. I still have not time to actually modify. Basically, it is I think maybe I will try to get it out by this week, and then I will brief you all later, because you have until about week 10 or week 11 to finish your assignment. And basically, I think at this point in time, you have to only find your partner for the assignment. Okay. So this is the learning outcomes. I've just posted the notes, lecture notes on this topic. This is an extension of your introduction to search, all the breadth first, all the simple search, classical search, breadth first, depth first, limited depth first, and the few other searches, and also the bidirectional search. So I think from there, hopefully you see some of the limitations of the such simple searches. And then for this morning, we talk about the heuristic search. So for this morning, we see a question there. Okay, no questions there. I need to check. Okay. The heuristic search, what is the definition? What do you mean by heuristic search? What type of searches will be defined as heuristic search? And the motivation for the heuristic search. The next part, we look at the simple 3D type of heuristic search. Before we move on to introduce your A star. Now, the A star or A asterisk is pronounced as A star, as seen here. And then we look at some of the examples of why search is so important in the area of game development and also drug design. Right? I mean, designing medicine to cure people, to help people who are sick. Now, the heuristic search, what is it? I've basically, one of the many different definitions, which I think is simple to understand, is any approach to problem solving. So again, it's about search is actually problem solving. Don't think of it as search as actually Google search. That uses a practical method. So it's something useful, something very useful. Or you can also call it a shortcut. A shortcut in order to produce answers, produce solutions that may not be optimal. Now, such answers, if you use such heuristic searches, may not give you the best answer, means the optimal answer. And optimal, we will again later on discuss what we mean by optimal versus local best. But fortunately, even though they are not optimal, but they are sufficient. They are good enough because due to the limited time frame or deadline, right? So with that given deadline, given time frame, that's the best you can do. So you don't have the luxury of many hours, for example. So you have to find the answer quickly, and this is the best answer within that time frame compared to even the other methods. Now, the heuristic search is able to solve a problem faster than your classical methods. Or to find an approximate solution. So it's able to find you a good answer and better than your classical methods, or even the better approximate answer. Good enough, approximately, you can use it when the classical methods cannot. Now, this is a kind of shortcut, as we often trade one of the optimality, completeness, accuracy, or precision or speed. What does it mean? It means that you are not, you have to trade. You have to trade in terms of you want the best answer. So, but if you want the best answer, it will take you 10 hours, but you only have 1 hour. So you are trading for speed. And you want accuracy of 99%, but if you use a heuristic, it will not give you accuracy of 99. It will give you accuracy of 95, for example, but it's much faster, right? So this is what it means. That's why you have these heuristic searches. Now, what's the motivation? Why do we need heuristics? So I think after the previous slide, it may be clear. One reason is to produce in a reasonable amount of time a solution that is good enough for the problem in question. I mean, within that problem, yes, it's the best you can do. It doesn't have to be the best. So it's not the best answer, but an approximate solution will do, since this is fast enough. So again, I show here it's a balance. So if you want fast answer, use heuristic. If you can afford the time to take 1 day, 2 days, or 10 days to find the answer, then you use the more powerful methods. But there's always a trade-off. So in engineering, it's always about trade-off. Whether you want a good solution, you pay more. So if you have a fast solution, you don't have to pay so much. So that is the typical type of problem you face in engineering. So let's look at the example of the heuristic search. So go back to the 3D search again of this map of Bulgaria. So this is a map of Bulgaria. So if you remember, we talked about this before in the previous lecture, where you have you're on holiday and your flight will leave from one part of the city here, Bucharest, and you're actually the day before you're supposed to fly off, you are stuck in a town called I think Iraq, somewhere over here. So you have, of course, when you're on holiday, you try as much as possible to maximize your time you spend discovering the country. So you're here, and of course you need to find your way on time to fly back to Kuala Lumpur, and from the city called Bucharest. There was a problem background while you're trying to find the solution, the best way, the shortest way, because it's the shortest way, fastest way, so you can maximize your time. You don't have to leave so early to Bucharest. You can leave last minute and still able to catch the flight to back to Malaysia. Now, for such problems, right? So we have a map of Bulgaria, but you have to reduce this kind of information here to something that the search can handle. And this is again typical of the type of initial work you have to do to reduce a problem that your method can process. Right? So this one, you find that your search cannot handle this. Right? You have to reduce it to something the search can handle. Okay, over here. And what else do we know? From the map here, you find that not every city has is connected. For example, there's no way for you to connect direct way, highway or whatever, to connect Erat to Niam over here. And see, maybe there are no bridges and no highway, so in order to go here, you travel to these kind of roads, right? So because maybe there's a river here, so maybe there's a different part of the city of different country, for example. So in order to go from here to here, you have to understand what are the limitations. So that here, this is the actual map that your search has to use. Meaning that there are bridges, there are highways that connect this kind of cities. So this is the actual information and also the distances of your intercity roads. So from Erat to Zerin is 75 kilometers, for example. And from here, Erat to Sibiu is 140. So let's look at the greedy search heuristic. So the greedy search heuristic, as shown here in the single quote, is you have to remember, I think we talked about this before, what are the 6 features of a well-defined problem that the search can find. So the first one, the starting point is you need to find your starting point. So the starting point will be here, Erat. Of course, you can also use the same algorithm to say I'm starting from Timisoara over here rather than Erat. So then once you have your starting city, you define what's the starting point. What's the starting city? So your starting city becomes your current city. Then you repeat this loop here until you have reached the destination city. So you must also know your destination city, where you are supposed to end your search. So this is the other important feature of your good problem for search to find the answer. So after this, you have to, from the current city, identify who are your neighbors. So if you're starting from Timisoara, who are your neighbors? You only got 2 neighbors here. Either you go Erat to the north or Lugos to the south east. Or here. Of course, you know the distance. So distance will be the measurement. Which one should I take? Okay. So and then you have to measure or get the information, the data. Now, if my next city is here, what is the distance? Right, so where should I go? So the next city you should go will be the one which is nearest to your current position. And this is part of that's why they call it greedy, right? You only take the nearest neighbor. So you compare. If it's Timisoara, you compare your neighbors, you have 2 neighbors, and then Erat and Lugos. And Lugos is 111 kilometers and Erat is 118 kilometers. So you have to figure out which one should I take. So you have this function to select the next city to visit. And once you identify the next city, then your next city becomes your current city. Yes, and after that, you check, is my current city my destination? For example, is it Bucharest? Right, so we say that if you look at example here, if it's you're starting from Timisoara, you have two choices, Erat and Lugos. So in this case, if you use that particular greedy minimization problem, you take Lugos. So you'll be 111 because 111 is shorter than 118. So as a result, then after that you take this point, and then if this point is this my destination? Is it Bucharest? Right? If not, you repeat this loop. Yes.
The issue. Can you go back to the map? Wouldn't there be a problem at Pitesti at the middle of that, because the shortest route is go back to the left, reminisce skill,
Yes, correct. But oh yeah, who did? At first I can't see you. Never mind. So you're right. Good question, good observation. This one may not be a problem if you're coming from this side, from the west. So if you let's say we start from here, Erat, the next one will be actually you go up north, isn't it? You go Zarin, because of the three neighbors, the shortest one will be this one, right? Zarin. After Zarin, you go up again, Oradi, 71, before you come down to Sibiu. After Sibiu, you have two choices, Pagaras or Renichu Welshire, 80. Now from here, you have two choices again, Pitesti or Craiova. So you take Pitesti. Of course, if you look at Pitesti, who are your neighbors? I think that's your question. My neighbors will be Renichu Welshire or Craiova or Bucharest. Now again, when you design that search algorithm, right? You also, how should I put it? Depending on the loop over here, right? If you take your next city, if you select your next city as the one which is nearest to visit here, you also have to put another loop, put another condition here. Make sure that you have not visited the same place, otherwise you keep going back. Doesn't make sense. So you have to say this Renichu Welshire should be eliminated from the loop. It means that you cannot go back to the same city, otherwise you keep going back. You see what I mean? So this has to be something that you need to put inside. I think this one it assumes that you will not visit back the same city you came from. Right? So it's out. Then of course, if you have two choices here, assuming I'm not going to Bucharest now, I'm going to Craiova. Right? So Craiova, if you are here, now what happens? So if you take the nearest one, you take Bucharest. But this second example, my destination is not Bucharest. My destination is Craiova. Now, but if my what do you call it? If you do not check whether the cities are any of them, even though it's longer, it's your destination, of course that should override. That should be more important than taking the nearest neighbor. So it's a matter of putting a bit of common sense into your algorithm. Is that okay? Is that clear enough? So as a result, depending on the order of your selection, if you say I will pick the nearest one first, so it will. If you do that, it will bypass. It will not go here because if this is my destination, right? So again, you go here, and then from here you go all the way here. So you're actually lost. You will not come back to this answer. So that is not a good solution. So when you design the algorithm for any problem that you're trying to solve, you have to look at your problem closely so that you do not make such silly mistakes, right? So you need to check, before you check the nearest distance, check whether any of these cities are your destination first before you consider anything else. Okay, does that answer any other questions? Let's see anything else from you guys. No? If nothing, I will continue. Good question. Where am I? Where's my? There it is. Okay, right. Okay, so this is your loop. So I think this is the simplest one. I think somewhere here, I think you rightly pointed out, if you have visited the city before, you must also eliminate that from the next city from the neighbors. It shouldn't be considered again. Otherwise, you go back to the place where you came from. And B, also need to check if your neighbors your destination. Then so you check your destination first before you check for the minimum distance. So it's actually it will make your method heuristic stronger, more powerful. Now this is what we call the uninformed greedy search, and this is a visualization of what we've discussed so far. So the problem is we're trying to find our way to Bucharest from Iraq. So this is a starting point. So from here, you have three neighbors. You can see here, Zerrin, Sibiu, and Timisoara. And these are the measurement of who should I select. Now we notice again, I keep repeating this. Every time you have find an answer to the problem, you have to be able to measure it, the quality of your neighbors in this case. Right? You have three neighbors. Who's the better one should I select? And all depends on your criteria. So this is an example of the minimization problem. There's also the what do you call it? The maximization problem. So you can also apply the same thing. Of course, not in this case because it doesn't. Since here we are traveling and want to be arrive at our destination the fastest time. So this will be an example of a minimization. We can also apply the same method for a maximization, but of course the conditions and the problem itself will be different. Okay, so here, obviously, who should I select? So I will take Zerrin, right? I take Zerrin, and then from Zerrin, then you have who are your neighbors. So in the case of Zerrin, if you look at the map again, you find that there's only one neighbor. In a way, there's two neighbors. Not to say one neighbor, right? The neighbors are actually Iraq and Oradi. But as I said before, once you actually come from Iraq, it doesn't make sense for you to say that Iraq is also your neighbor. So in this case, there's only one neighbor, which is Oradi. So there's nothing much to consider. You have to, just pick Oradi. For Oradi, same thing again, right? You have no other neighbor, so you have only Sibiu. And from Sibiu, you have two neighbors now. Rimini, Shu, Welchia, and Fagras. So of course, it's easier to, from here, clearly, you take your RV, Rimini, Shu, Welchia. So I can see here, what do you all see? So I can point out to you, clearly you can see one of the weakness of this method. Notice here.
What?
Oh, sorry.
What?
See that? See that? It taken it 75 plus 71. This is 1, 4, 6 plus another 1, 5, 1. Right? To arrive at 2, 9, 7 at Sibiu. Now, if I had taken from here, Iraq, go to Sibiu, I only travel 140. So in a way, it's faster. But because this method relies on the nearest neighbor, which is greedy, so it actually, in a way, is blind, uninformed. You see it? So it's uninformed and blind, so it cannot see anything else. So that's why I still arrive at Sibiu, but after taking this, such a long way. From Sibiu, what do? I now pick Riminishu Welchi as my next city to visit, to go. And from there, I have two other choices. Pitesti, Craiova. So in this case, since Pitesti is nearer, I take Pitesti. And then from Pitesti, I think there's only one path, which is your Bucharest. So total path. So you need to show the quality of the solution of this path, going from Iraq, Zerrin, already. So this is a path. You trace it back. And this one, so the quality is 575 kilometers. Okay, now this is the research. Now, I want to also now talk about another method, which is your example of what we call the informed search.
Oh, Sir.
Yes.
The second
Please.
method, the CBU just now, it won't reach the other options.
CBU,
yeah.
Clear, right?
Yes. So
what do you
the
mean?
second option on top, just before Arad, I mean like right after Arad, won't it have the Reminutio and the Fagaras option also? Or is exclusive to that one only?
Okay. Arad, because I think very careful here. You have to look at the method here, which is the research. Research says that here. I'll look at the neighbors. So in this case, who are my neighbors? Next thing is how do I select my neighbors? You select the nearest one. So you can only see at this point. But for us, we can see the whole map. Right? But here we cannot see. So please remember, that's why we call it a blind search.
I see.
Uninformed. It can only see its neighbors at this point in time. So every time you move, you can see the neighbors. So you keep moving. Okay? So that's why here, I mean, as a human can see, of course, if you have the whole picture, you see that it doesn't make sense for me to go upside, go north and then come down. So straight away I go here. But if you say that it's better to go straight here, now I can see that you have done some calculations. You say that if I go straight here, even though I violate the rule of my research, that means that I do not take the nearest one. I take the longest one, 140, right? 140 compared 118 compared to 75. So I take this one, but of course I violate the rule of this method. I should take the nearest one. But then you have to defend. You have to explain why you take CBO, because I said if I take CBO, it's only 140. Now if I take this way up north here and then come down, I have 297, right? But of course, that is not the point. The point is because of this method, it's based on nearest neighbor, the shortest neighbor to your current point.
Okay, I see, sir.
Of course, we are only covering the very basic one, the method here. Of course, there are other more powerful methods, but this is, as I said, introduction to search. Now, the second one is because of this uninformed search, you can clearly see some of the limitations, the weakness of this method. So better search will be what we call the best first search. It's a type of heuristic search. Now, you will still need to evaluate the points generated during this search, neighbors or whatever. So some will become clearer later on. And of course, you still have your evaluation function, meaning that you have to figure out which one should I take. Now, this one is actually convention, the lower f, the function here, the measurement. So which one should I select? The lower the f, you should pick the one, select that one with a higher, with a lower f. So with a higher f, it indicates a more difficult problem. So of course, because of this, you take you select or go in the direction of when the f value is lower. Let's look at it in more detail in the next few slides. What I mean by that. Now, it combines one of the important characteristics of your best first search is that it combines the advantages of your breadth first. Remember, the breadth first actually goes sideways before it goes down. So it combines the advantage of your breadth first and the depth first search. Now, in your depth first search, right, DFS, it follows a single path and don't need to generate all the competing paths. It just goes straight down. So you don't care about whether it is a nearest or whatever. As far as the BFS is concerned, it just goes deep, go down. Now, on the other hand, the BFS, the advantage is that you won't get caught in loops or dead end path, because if you go down all the way, remember in the last lecture, you can clearly see that if our destination is over here and our depth first goes all the way down here, you end up at the dead end, right? So it's no good. Now, this best first search or best first search, you explore. Actually, this is actually not the breadth first, it's actually the breadth first search. Explore the most promising path seen so far. It is still exploring. It doesn't guarantee you it's the best answer, but still trying to explore which one is the better path for me to take. Like just now, the greedy search again is exploring, searching. Now, while the goal is not reached, what happens when the first search has not arrived at the destination? Then it will generate all the potential successor states. That means that it will tell you if the current position is not the destination, it will tell me what are the other possibilities I can go, and then add on to the list. And of course, similar to the greedy first, it will also pick from the list itself. It will pick the next best state or city to visit, and then go on from there. And then that again, you repeat the same process until you end up with the destination state. It's also similar to the steepest ascent. That means that you go down the one which is the easiest path, steepest one, just go down. But you don't throw away the states that are not chosen. So you still keep a record of those other potential answers that you have. Okay, now this is the same map we have seen about 3 or 4 slides just now. But notice that on the right-hand side here, I have what we call the straight line distances to my destination called Bucharest. Excuse me. So now my starting point is Iraq, right? I want to know from Iraq straight line to Bucharest. What's the distance? So Iraq to Bucharest is 366. How about Zerrin to Bucharest? What's the distance? Zerrin will be somewhere down here, 374, right? And then you do the same thing. Notice that notice that there's no such thing as a straight highway from Iraq to Bucharest. You have to pass through all these other cities. So in that sense, it is it's not real, but it gives you a sense of direction. Where is my direction, right? So if I'm so in that sense, and you notice Zerrin and Iraq. Zerrin is 374. Zerrin, this is 374. And my Iraq to Bucharest is 366. So in this case, if you apply the same selection criteria, shortest one, I will take Iraq. Early on, when we use the greedy first, I will take Zerrin. So there's a slight change here now. When I use this straight line distance as my measurement to select my next city to visit. So this is quite a useful list. So now the best first will not use this distance of 75 or 140 or 118, right? It will use these values here, which is the straight line distance to Bucharest. Notice that as a result of this, Bucharest to itself is 0. Yes? Okay. Now, how does the greedy, we still call it greedy, but it's a best first search. So you have to, first of all, find out, you have to compile the list, which is an estimate of the cost of the distance from your current position to the destination goal, which is this list over here. So you have to generate this list in order for the greedy best first search to work. So again, this is example of this problem. Then in example, in this case, we have to generate the straight line distances from your each city to your destination goal of destination city of Bucharest. Now, greedy best first search will expand the node that appears to be the closest to the goal. So notice that we highlighted the word appears. As I said before, this one will tell you roughly this one's Sibiu seems to be nearer to Bucharest compared to Zerrin. Now, what is Zerrin? Zerrin is 374. How about Sibiu? Sibiu is 253. So it tells you that who seems to be nearer to Bucharest of all these cities over here. So we have 3 cities here: Zărin, Timișoara, Sibiu. So you still have to identify your next city to visit. Yes. So you have your Zărin, near from Arad. You cannot simply fly to Bucharest, right? You have to go to Sibiu first, for example. So in this case, where can I go from here? There are only 3 choices: Zărin, Sibiu, and Timișoara. So which one should I select? In the earlier 3D searcher, you take the nearest neighbor, which is Zărin, 75. But in this case, we take the nearest city which appears to be nearest to Bucharest, which is Sibiu. So yeah, actually, in this method, actually, if you can look at it closely, you can see that this greedy best first give you a sense of direction. So if you are traveling to the east, which is Bucharest, it doesn't make sense for you to go north. Yes, so it doesn't make sense for you. So in that sense, it is common sense. So they call it heuristic to take Sibiu rather than take Zărin, right? And this is something that the scientists have come across. After looking at this problem, it doesn't make sense for me to go up north. Why should I come? So what should I do? So you take that. In that case, I have a sense of direction encoded into each city. So I take Sibiu now rather than Zărin, right? So appears to be closest to the goal. So again, this is a visualization. So I have shown here the actual map of the problem you're trying to solve, and then this is the straight line distances from Arad. So Arad, we know that Arad is 366, right? Straight line distance to Bucharest. So from Arad, you have 3 choices, right? Now notice here, I do not put down 140 anymore to Sibiu. I only put 253. So I use the values of the straight line distance here over here. So how about Timișoara? Timișoara is 329, and Zărin is 374, right? I do not use this table anymore, but this is only for our reference to see how this thing actually works. So here from Arad, I will pick again. You still have to select which city to visit. So of course this makes sense if I will pick the nearest one, which is Sibiu. Nearest in the sense nearest to my destination, right? Not nearest to Arad, but nearest to my destination of Bucharest. So after Sibiu, what choices do I have? So yes, Sibiu is here. I have few choices. I can always, Arad, but of course this one should be eliminated. It doesn't make sense for you to go back to Arad. So this one shouldn't be here. Should be eliminated. But at least for completeness, we list it down here to show you that these are my neighbors. Now, from Sibiu, what are my neighbors? We have Oradea over here. We have Rimișu Vâlcea is over here, and then your Făgăraș over here. Now, of all these 3 cities, which one seems to be nearer to Bucharest? So again, you look at the values. So for Făgăraș is 176, Oradea is 380, and RV is 193. So fortunately, you take Făgăraș. So actually, look at these 2, almost the same. Right? But of course, this is slightly closer to Bucharest compared to RV over here. So you take Făgăraș as my next city. So from Arad, Sibiu, you go Făgăraș. So from Făgăraș, again, for completeness, you put Sibiu as my neighbor, and then you have Bucharest. So you can see after this, 1, 2, 3 cities, and you're done. Compared to the early one, you have to travel Arad, Zărin, and then go here, Sibiu, and then you go Pistachi and Bucharest and things like that. So you can see this seems to be much more effective. But again, the concern is the sort of concern is that this will not work all the time. It depends on your problem space. So this one is showing that on a good day, this one can be much better than your 3D search. Of course, after you find your answer, you trace that, tell the driver what to do. So, alright, you travel to Sibiu. This is your, a bit like your Waze. You run your Waze and then Waze will tell you how to, what's the best way. So, it tell you from here, you go here, you go here, and go here. Okay. So, that is one example of your best first. So, let's look at another example. Now, in this case, this is actually, for those of you who are familiar, this is a map of UK, United Kingdom, showing all the major cities of UK. So here we have to find our way from Birmingham down here to Edinburgh, up north. So again, you have to figure out the direct distances, right, to Edinburgh. So you can see here, Edinburgh to Edinburgh is 0. Edinburgh, Birmingham to Edinburgh is 39p. So from here, so we have a few choices. So we can see here, in this example here, there are many more choices. From Birmingham, I can go to Cardiff, I can go to Plymouth, London, and also go to Norwich, and Hull, Manchester, Liverpool. So we have 1, 2, 3, 5, 6, 7. Now notice that in the case of Cardiff, right, it's Cardiff to Edinburgh is 500 kilometers. Plymouth is 620. Liverpool is closer. Now, that's one part. The second part is you look at the actual intercity distances between the neighbours and Birmingham. Liverpool to Birmingham is 147. Manchester to Birmingham is 134. Right? So, still all right in the sense that you should take Manchester. Right? You can also have a case in between that from Birmingham, the Oxford, it's not listed here. Oxford maybe is nearer compared to Manchester. So you can also, if you take the greedy search, you can go to Oxford. Oxford is nearer to Manchester compared to Manchester. Can also happen. And this is fortunately, you find that right. So you have this one is very interesting. Now if you just look at the direct distances from each of the neighbours, Liverpool, Manchester, Hull, Norwich, and so on and so forth. 1, 2, 3, 4, 5, 6, 7. 7 neighbours here. You find that which is the nearest one to Edinburgh? You have two similar choices, Liverpool or Manchester. You see it here? So if you take Liverpool, is actually 280 kilometers to Edinburgh, the same as Manchester to Edinburgh. So what happens in such cases? In such case, you have to what is the solution you think? So the algorithm will have to toss a coin. Because either one is okay. As far as I can see, of course you can see it, humans can see it, but if the AI cannot see it. So it will just randomly select one of them, either Manchester or Liverpool. When you have faced with similar choices to visit. So if you are lucky, you end up with Manchester. If not so lucky, you end up with Liverpool. So you can see here, the length is Birmingham 390 to this. I think this is actually how you can write the program for it. And then you have to select the neighbors. So you have either Liverpool or, so in this case we take, I think we take Liverpool is 280, Manchester 280, Hull is 310, Cardiff is 500, London is 530, Plymouth is 620, and so on and so on. So in this case, we take unfortunately we take Liverpool, right? So we take Liverpool, and from Liverpool we have choices of Manchester. Obviously, we can't go back to Birmingham, so we have to take Manchester, right? And then from Manchester, we have two choices. Here and here. So now Gala is 110 and this is Hull is 310. So it makes sense for you to go up here rather than go sideways. You can see here. So the best first search actually gives you a sense of direction to move rather than going sideways here and going the wrong way, so it's nearer to your goal, the destination. So from here, you have two choices, either Glasgow or Newcastle. So since Glasgow is closer to Edinburgh, only 70. This is actually twice the distance, so we take Glasgow. Right, so of course, you end up with the answer. So this is your Birmingham, Liverpool, Manchester, Carlisle, Glasgow, and Edinburgh. So this is your final path, so-called your ways that will find you the way to go to Edinburgh. This is the second example. Right, so after you do that, you also need to be able to measure, right? What is the distance? I've plotted here. So you go Liverpool, Manchester, Carlisle, Glasgow, Edinburgh. So you also need to able to assign a value, the total distance of 625. Now, if you have been lucky, when you actually selected the two and you take Manchester, you'll be 551, right? So this is a better one. So of course, you can see that it's still not perfect. It's still able to find the best answer compared to a human. A human will actually calculate, do all the calculations, say that this is actually closer to here rather than here. But as far as the 3D best first is concerned, when you're faced with such similar choices, you just randomly take one. The word is randomly. Okay, now, so far that is your, what do you call it, your 3D best first. So it's clear that the 3D best first has a bit of problems. And of course, we move on to the next one. Now, can we take a short break? Do you want a break or you want to carry on? I think last time you all wanted a break, a short break for you to digest and take maybe a toilet break or whatever. So we take a 5-minute break and then come back. Okay, thank you. Yes. Any questions? Those of you want to have questions can still ask. Otherwise, I'll also take a break. I think I'll be sitting here this whole morning since 8 o'clock. Okay, I'll also take a break and then I'll come back 5 minutes time. Thank you. Okay, I think can we continue? Meanwhile, can you check your chat group? I've written a short quiz for those of you affected by the public holiday on the 20th. Can you please fill up this form, and then from there I will decide what's the best way forward. So only for those affected on the tutorial on the 20th of July. Now let's go back to the question from Chung Yi. How does the best first search determine? Determine what? Determine. Let me check. Determine direction in the. Determine the what? Determine the. Is in match to destination. I think. Although I said. Chungyi, although I said this one gives you direction, they actually go back to here. Where's my phone? Okay, back to here. It doesn't really. It doesn't really give you direction, but when you get the shortest distance, straight line distance from any point to the destination, okay, let's try. If you are now at Sibiu, that is your starting point, rather than Erat. Now, I still want to go to Bucharest. So if I were to calculate the straight line distances of my neighbors, which is already Erat and Bucharest and RV over here, right? You can see that if I'm moving away from direction, moving away from Bucharest, Erat, it actually has a longer distance compared to Bucharest, which is nearer. So in that sense, it gives a sense of direction, but it doesn't really determine the direction. As far as the best first search is concerned, it still looks at the neighbors and only looks at the distances, straight line distances, as an indication of the direction. Okay, does that answer the question? Let me see. I will go back and look at your I'll look at your reply. Let's say. Okay, I got the 15 answers already so far, but I will compile the answers and then maybe come back to you next week. Okay, to look at your what is the choice? Actually, a large percentage, half the class actually say continue lectures on the 20th, and then the RMH, I think a few of you wanted to have it on the 27th. So I think it's still okay. Those of you who want to continue on the 20th, I think I will see whether it's RE or RMH. If it's just all the RE students, then we will. But again, I can see already there's some RE students who want to have the tutorial shifted to the Thursday. So I think I cannot force those who actually want to join. Maybe there's something on. So looks like RE students, you will have to join the Thursday morning tutorial, because there are some actually wanted have it on that day, right? Have it cannot wanted to shift it to Thursday morning. Okay, but I'll talk about it later on. Let's come back to this. Okay, now, so Chungyi has a question. Further question is like checking whether the node is further away from destination. Yeah, correct. So based on the neighbors and also the direct distances to the destination, it will try to move in the right direction during each move. So it's still the shortest direct distance to the destination. As I said, it doesn't It doesn't give you a sense of it. You're not measuring direction, but there should be something you can also incorporate. But as for this best first search, it doesn't include direction. But the direction here, when I say direction, is in the form of the straight line distance to the destination. That's what I meant. Okay, let's continue. Jung-Yi, we'll come back to this later, if you don't mind. If you come back to this. So we have finished this. I think this one should be quite... okay, now, the A star. So we have we can see already some of the problems with the greedy search, which is just the nearest neighbor. And then another one is the best first search, which is looking at the direct distances, direct straight line distances to the destination. Now, A star is the combination of both, which actually is derived from the best first search and uses two measurements, which is your G of n and H of n. Now, what are these? So we come to this later on. And actually, A star is better because it's optimal. It gives you the best answer and it's also complete. Now, it's a Gn. If your Gn is 0, means you don't consider this, you only consider the Hn, which is the nearest neighbor. So if this is not taken into account, then A star basically is the same as your greedy algorithm. It always picks what looks like the most promising path to the goal, nearest neighbor. On the other hand, if your H naught is 0, you only consider G of n, right? So this one will be your breakfast. So it looks at the straight line distances to the destination. See the cost of each path will be the length of the path. So this is your, so you can have a play with both. So actually A star combines both the greedy search and the greedy search and the breakfast search, right? So how do you do it? So you have the A star. So this is the formal definition of your A star. You have to look at where's your starting point, and then where can I go after this? This is your priority, right? So priority is based on your function f. I can show here. Basically, fn is actually gn plus hn. I think later on we'll come to that. Your function f. So while the queue is not empty and the goal not found, right? So you still have neighbors. I want to highlight this. Sometimes your queue can be empty. That means that you have no other place to go. Yeah. Let's say for some reason you arrive at Niam. We are here now. So from ERC, we arrive at Niam because imagine you are coming here all the way. So was Louis, you have ERC, and then you have Niam. Now, after this, who are your neighbors? Right? So since you just came from here, so who are neighbors? So in this case, the queue is empty. You have no more neighbors. So you come to a dead end, and Niam is not your destination too. So Niam is not your destination, and Niam there are no neighbors. So the queue can also be empty. That's what it meant. The queue can be empty. Clear? So as long as the queue is not empty and the goal is not found, you keep repeating. Right? You get the best state from it. You select the best city to visit after this. Right? So if not the goal state, then you generate all the possible children. That means the next state to visit, right? And save the information for you to evaluate. And you apply, you calculate the function f for each of the new nodes, and then you select which node to visit to add on to your solution. Of course, make sure you also remove the duplicates from the queue, right? So again, using the f function to select the best next node to visit. This is one. So you can see FLN is here. FLN actually is a combination of the GN plus HN. Now, what is your GN? What's the HN? Now, you can see here, GN is actually your neighbor. Let me see here. GN. Correct. So your G is always 1. So your GN is actually your this is your destination. So your GN is actually the distance to the nearest neighbor, and then HN is actually the distance to the destination over here. So you just add the two values together. So now instead of using one value, you have two values now. You combine the two, and then you so this is better. Obviously, clearly see is better than either the greedy first or the best first search. So G of n is known of the nearest neighbor, and this one is actually the estimate of your straight line distance to the goal, to the destination. So this we call it the heuristic guess. So in a way, the A star is also a part of the heuristic search. So this is another example. Now we apply the A star to this method, to this problem here. So this is a source where you start, and I can see here that in addition to the distances to the neighbor, each pair of cities, you have also the straight line distances to the goal node here over here. So you basically from S you have what 9 and 7, right? So you can see here because the can see here E is actually further away from this node. This is L, is it L? I think L or T, yeah. Whereas this is A is nearer here. That's why the distance, straight line distance from A to L is 5, E to L is 7. Although both of them have the same city distances to with S. Of course, you take A now and you perform the same thing, repeat the same process until this state. So imagine if you've taken, in this case, if you're taking this way, because over here, you cannot come back to this path. So this is you see that A star is able to now find you a better solution compared to either the best first search or the, no, best first, I think you still find this one, but the pre-search, obviously no, because this search will only take these two values, 2 and 2, then you're up to you to randomly select one of them, and you might end up with this chart over here. So you can see here, that's how it works, right? A star. So we have 2 plus 5, 7, 2 plus 7. This is the E, 2 plus 7 equals to 9. So you take this one. And from here, therefore, then actually this one, there's no, from B, you cannot connect back. Right? Connect back to F. So it's all the way down here. So we end up with this one, right? So this is your destination here. Now, again, let's revisit our holiday trip to Bucharest and then come back to fly back to Malaysia. So again, here you can see now, in addition to the inter-city distances, now we have the straight line distances to Bucharest. So you can see here. Okay, so in this case, you can see I have my neighbors over here. So I can have then you have these straight line distances, like as shown here, straight line distances to my destination node, which is the Bucharest over here. Right, and this is the straight line distance. So what is the downside? What is the disadvantage of your A star and your breakfast search? You need to be able to compile these straight line distances. So you have this additional information, so there's a cost involved. So you need to be able to find this. If you cannot find this information, you cannot use the A star nor the breakfast search. So once you have this information, you can then use it. So basically, the message is if you try to solve a problem, try to find as much information as you can about the problem to help your AI technique over here. Oh, if you use A star, what happens now? So A star is a heuristic and it's a bit informed. So you can see here. So you have your A star, Erat, to Zerin, Erat to Sibyl, to Nosora. So over here you have your, I think this is probably add together already. Yeah? So this is your Sibyl. So we have again you take you combine the two values, then you take the shortest one, this is 393. And you take and you from here 275 and 273. You take RV, this is 273. Although this one again makes sense because 80 is nearer to but in the earlier one, the 3D search will never take CPU because CPU is 140, right? I will take Zerin rather than CPU. And from RV, you have Craiova, which is 306 or Pitesti 197. Then you see straight away on that, right? What's the total design or something like that, right? So now you can see the tremendous improvements to the search from 575 to now we have 418. It's so much faster compared to this. Because to avoid this problem here. So I've also done a study of this problem. So this is your first one using your research 575. Now the 418 is your A star, which is here. Then you have something also called the local optimum. It's another solution. You can also come up with that. Instead of taking ERA to Zerin, you take ERA to Sibyl. But over here, instead of going to RV, you end up with already. So this one is 450. Of course, the best answer is 418. So what we call global optimum. So this is the best answer, and there's no other answer better than this. At least for this problem. Of course, it's not easy to find this global optimum, although we always try to find the global optimum. This is the best answer. Now, come back to this. What do you mean by local? What do you mean by global optimum? Right? Local. You have a local optimum, and then you have your global optimum. What do you mean by that? So now I'm giving you here, if you're standing on the hill, this is your observation point. You're standing here, and I ask you, where is your lowest point? So you look at your left, this point here, and your right over here. Any questions? I see someone turn on the microphone. I hear someone turn on the microphone. No? Let's continue. So you can see here, based on the observation point, you can see that I can't see beyond this. So this looks like it's my lowest point. Right? Now if the same thing applies, right? So can see that if I'm standing here, I will find that this is my best lowest point. But if but I know that this is not the lowest point in this space, over here, because this is the lowest point in this space. If this is my search space, I want to find this point. This is my lowest point. This is also known as a global optimum. Now this point will be my local optimum. This is my global. This is my local optimum. So in a way, as I mentioned before, this will be your country champion, smallest one. But this is to be the best around the world, international or global winner, or global champion. Now we are expanding it. So question is, how can you always get the global minimum, global best? Right? Would you want to have only the local best, right? So how can I always get? I want to always get the global minimum.
You get all the data. I mean, like if you have all the data, then technically you have the global. You can choose the global from them.
Correct. But the question is, it's not easy to always get all the data, right? So that's why later on you find that from the methods that you want to explore, you find that they always tell you that you will not start at the same point. Because if you always start at the same point, you can only find this. Of course, your comment is correct. I need to find what does my search space looks like. But again, the search space can be very large. So large that, and later on I will show it to you. This is only how many dimensions is this? This is 2 dimensions, right? Your X is over here and your Y is over here. Imagine if you have 15,000 dimensions. I can't even start to imagine what it looks like. And to find find all the information is almost the same as finding this point here. By the time you find you can map the whole space here, you can actually find the answer straight away. But to map the whole space actually is not feasible, not practical, because it takes too long. That's why we have these heuristics and other methods. So my point is this: very steep, right? So it depends on your observation point. If you want to find, at least try to find the global minimum. In this example, of course, you can also do the same thing with global maximum, right? So you can see here, if you're here, this will be your local minimum. This will be your global with respect to this search space. I always highlight this. It's only somewhere over here or somewhere over here. This answer may change because it depends on your search space. That's why it's very problem dependent. Right, now let's look at any question before I move on to the example. I think we're coming to almost to the end already. So this is 2 case studies. So to show to you that search is not only to search for information like Google or to search for how to go from point A to point B. Search can also be used in game development. Now, this is actually Mr. To Seng Chun. Actually, he actually was my student actually during his internship. He's a student from computer science in University of Malaya. So I asked him to develop using AI. He using AI and heuristics in a game called Othello. Right, Othello is a 2-person game, and I'll show you what it means. Right, it's a very simple game. Basically, another name is actually flipping it. Right, so by flipping, so you put another new we call circle here, right? Token over here. If you're playing black, you put a black here, so flip, right? Then all this become black. Then when it comes to your opponent, this is using the white tokens, right? So the buttons are white buttons. Then you see that this all black. I flip over here. I flip this one, become white again. So I thought, no, come on. I cannot. This is black. So I can only have I can do a white here, and to flip to white. So I have a 3 and a black is a 3. So that's how we play the game Othello, right? So simple game. So it's a 2-player game on an 8x8 grid. So the size of this space, if you can call this also a search space, it's only 8x8, quite small. So objective is to collect. So there's a question from Chung Yi. Okay, no, this is I think something else. I think I saw the old message. So you have to collect as many points, as many colored buttons as you can. So the winner is the one with the highest number of buttons in this game. Now this is actually the game, but this game was actually revised with the modern rules in 1971. Now the starting position is fixed. So I think in the earlier version, there's no fixed starting position. So this is fixed at the center of the board. In this case here, so it's at the center. It's always 2x2. So you either select white or the black. Simple game. So what happened was that so simple to play. But I think going back to the question here, the actual search space is as big as 6,461 possible patterns in just one line of row or column. Just one line. And then if you look at the whole board, there are actually 6561 to the power of 8 or 3.433 to exponential 30. different board combinations. So these are all the possible combination. So if you can match the combination, of course, you can then decide what should I do after your opponent has make the move, right? In order for you to win. So you can just refer to that table. But that table is actually huge. So question now is, how do you store such big space? Now, one other thing I remind you, for the 8x8, it's not a very large problem space. So 8x8. So imagine if a problem is actually increased to larger, maybe twice or 10 by 10. Not that large, but in the real world, it can have much complex problem than this, as you will see later in the next study that we have later on. So if you, again, same thing, if you were able to calculate each of the solution, possible configuration, what you call it, the pattern for each board, right? Then you have to count if there are actually 3.433 to exponential 30. So it will take you 23 years to calculate all the possible calculations to find out all the search space. Again, it's due to time. So that's why in the past couple of years, there's been some work done to replace such computing, right? Our computing is based on what? Based on the von Neumann's machine, right? Which is on what we call the what do you call that? This what do you call that? This what do you call it? Transistors, IC circuits, where you shrink every 2 years, you shrink it a bit. But that's why there's some research going on to actually investigate what is known as quantum computing, right? So it's based on quantum mechanics, which is a computer. That one, if we can develop such a quantum computer, we can then, because it's very fast, then you can actually do this, which is what we call the brute force method. That means that I look at first of all, I compute all the possible board combinations. Then I use it as a lookup table. So if you take any move, I see, you are here, so I will take this move, and then I look at the board again. But I need to take it's not even 23 years, 1 to the power 23 years. So it's a large number of years to calculate. Even if I take 1 second, of course, you can say that it takes much faster than that. But I think 1 second is not that slow, isn't it? It's quite fast already. But then of course you say, I think I can do it in half a second. But half a second is still 0.5 exponential 23 years. So it's still a lot of time. So that's why you can see, because of this time constraint, our current computing technology cannot cope. That's why there's some work being done to actually look at different kind of computers, which is a quantum computer, even optical computers, as an example. So the rules are simple. So the black player always starts first, and then you flip. You flip, and then as a result, you beat the user. So these are the rules. So when you start programming it, when you start to write a program, intelligent program to play with a human player, you have to follow these rules. So is this a trivial problem? No, it's not a trivial problem. Why? Because a couple of years ago, Michael Burrow, he actually his PhD. After he graduated, he went on to a postgraduate degree, and he developed this Logestilo. And then his Logestilo earned him his PhD, his postgraduate degree, right? And a couple of years ago, when I checked, he was actually working for Princeton University at NEC, a Japanese computer manufacturer, in research lab at Princeton University in the US. The search space, other than the legal, also has illegal move, which you cannot make the move. So the representation of the problem is they have empty, represent 0, white is 1, black is 2. So that's how you actually represent the problem. You need to reduce the problem. You need to reduce the problem, and then Sorry, it's a background noise. Outside people cutting the grass. So we have this representation. So of course, in any problem, you need to reduce the problem to representation that your computer can program. And as we said before, it has a very large search space, right? So again, our search space is not as simple as this, right? So this is a simple two-dimension. So in this case, you can have so many different large search space, right? And then of course, as I said before, you cannot use such brute force. That means that you look at all the combinations first, and then for you to select use it as a lookup table. It's not possible because it takes too long to actually calculate one answer, whereas I don't calculate for you. This is actually I think we've seen this before in the crosses and knots. Remember the first lecture we talked about this before. So this is similar to that. So if this is the initial, this is the initial state. So we have legal move highlighted in red here. So we can either, this will be the zeros and this will be the knot. This will be the zeros. And this one will be the, okay. So remember, in this case, we assume that the zeros take first. So zeros, you can have either 1, 2, 3, 4. So we have these 4 places which is legal for you to take a move, to state your move. So you can either put your button here, the 0 here, or the 0 here. You put a button here, it will flip. This one become a 0 as well, or can be here. Now, once depending on which one you take, if you take the 0 over here, then this will flip this one, all becomes 0. So we have 1, 2, we have 4 buttons, or 4 tokens of 0. Now, if you take the one at over here, so this will flip this one, and of course, so we have 4 possible states. Now, clearly you can see that from 1 I can generate 4, and from here, this 1 I can generate another 3 more. I can put it, so I can put it over here. No, sorry. This move is what? This move will be the crosses, no longer 0. So this one is the opponent's move now. So the crosses can be put here. The crosses can also be put over here, right? So you can also do diagonal over here, or you can also do horizontal over here. So here, for the crosses, you can have three choices, either here, here, or here. So from 1 here, then I think the same applies to all these 3. So you can see here from 1, 4. The next level will be 3 by here 9. So 4, 9, and it goes on. So what do we do? Seng Chun actually used it. We search around. What you all do some literature review, see what method works well, and find that the Minimax algorithm works well. Minimax, what is Minimax? Minimax is a technique that attempts to take into account your opponent's best move. So you try to guess what your opponent, your competitor will do, the best move, and yet still give you a winning strategy. So what happens is that the human player, you pretend to be a human player. The human player will attempt to minimize the score, whereas the program now, the program you're writing, will try to maximize the score for the program, right? So Minimax is a depth-first search, which follows each possible path down to a given depth. But of course, it's limited, because if you don't limit your depth-first search, it can go forever, going to that path, and the path is huge, as you may have guessed from the earlier. Yeah, if you imagine you go down all this way up, so you can see that you will go very far down. It's quite deep. So this is basically the essence of the Minimax. So this is the user interface of Seng Chun's Othello. And then you can see that you can actually the program is actually allow you to, so we actually written the program in Java. So it's a nice little program. But now I don't have the Java installed on my machine, so I can't show it to you. Now, other than that, some example in game, you can also have a search in drug design. Now, this drug is not your haram, not the drug or I think make you feel good. It is actually in curing people of certain deadly diseases. For example, what do you do? So this, according to Pfizer, and of course they have all these other companies making drugs, medicinal drugs all around the world. Drug discovery, to find a new drug, is very expensive. It's time-consuming and very risky. Not really risky, it's very risky. Why is that so? Because you try certain things along the way. It takes you maybe 3 or 4 years and find that, hey, it doesn't work. I think you look back at the current situation of the COVID-19, is actually we are quite fortunate to be able to find the answer and find at least some answers so quickly, and also so quite successful. So let's see. So it's complex, lengthy, expensive process with low success rates. What it means that you actually find that. Okay, I'll show this next slide. I think there you go. So the drug discovery, to actually develop new drugs, as what you call 5 stages. First of all, you have to do a discovery stage. This is, I think, the standard process. That's why you find that some of the controversy surrounding the current COVID-19 vaccines. We did it within 1 year, right? So that one, I think there's some controversy over that. In the past, the standard process is that it takes 3.5 years for you to come up with a certain potentially effective drug. Take you 3.5 years. Now, during this stage here, 3.5 years, there's about less than 60% chance that you'll be successful, 40% chance you'll be failures. So, in order to actually get one successful new drug, you need to be able to generate 30 potential new drugs just to get one successful drug launched at the end of the day. Now, then after that, we move on to what we call the preclinical stage. This is about half a year, very fast, and the chance of failure is actually I think this is actually not chance of. I think the chance of failure actually is 35%, and then to need 13 projects in order to get one. So from here, hopefully you get 13 left in order for you to have one at the end of this process here, and it goes on. So after that, you have the preclinical. Clinical will be whereby you actually test it on the human subject. You have clinical 1, clinical 2, and clinical 3. And each of these takes time. 1.4 years, 2.3 years, 5.1 years. So it takes about 2, 7, 8, about 9 years for the clinical 1 to end clinical 3. So hopefully by then you get 1.7 left, right, in order to reach the end, and until you have finally one drug successfully developed. Right? This does not list the cost. This does not list the cost. Now, putting this is only on time. How much does it cost to actually do one drug, right? So, in order to get one drug developed, this is, I think, in USD, $2.6 billion to successfully launch one drug. So it's a very expensive process. Right? So it's actually part of cost per project, 20, number 30, and cost per successful project. So you can see $609 for the project. Right? So we have got cost involved. So this is on drug design. Now, currently there's some different way of looking at this. So we want to get a drug that will hit at the right places, right? So major aim of drug discovery is to identify which are the areas, the bioactive molecular structures that can be used to find the bioactive molecular structures that can be used to cure certain diseases. This is what we call docking, about how this is actually running docking simulation. So we don't, before you actually run it on humans, you try simulation first to try whether the drug, see the drug or not, has able to bind, right? This one is clear, right? So it's actually 10 to the power 100 set of chemically feasible drug-like molecules. So there's a sort of large pool of possible chemicals that can give exist, an appropriate molecule for almost every type of biological activity to help you to become stronger, run faster, things like that. So there's a large number. Now, the challenge is to find such molecules. But of course, again, you cannot use an exhaustive search because it's very large. So that's why you need to rely on AI. AI search strategies to find the correct drug to bind to the correct surface of the molecule of the human cell. One quick solution is randomly search. It's simply tembak. You do a random search. It's one workable approach to solve the task. But the extremely large search space, again, because of the large search space, if you simply randomly try, chances are the chances of your success is very low, still very low. But of course, it's fast. You have a possible answer, but of course, the answer is no good. So, of course, you want to do that. So now, this was done about 10 years ago. This was actually I think some of this is still relevant. These are the hot new markets. If you can come up with this to handle, you eat a lot and you still become, you do not have to be, you will not grow fat. Or, diabetes. Diabetes is a major disease when the body is not able to process the sugar, and also other metabolic related diseases. So this is a big market for such diseases in humans. Imagine if you have a drug that I can eat a lot and yet not fat, or after I'm fat, I can take this drug, I'll become slim. You can have a huge market for that. Alzheimer's disease. What is Alzheimer's disease? Basically, it's a memory disease. That means I cannot remember things. I can't remember my parents, my family, my loved ones. So this is Alzheimer's disease, and it's actually quite a major killer. And so it's I won't say it's a killer. It's actually a very bad disease in the sense that you don't die from it, but you actually become you can't recognize people around you. And of course, the next one is anti-aging. Right? You still look young, even though you're 80 years old, 70 years old. So by taking this special pill, I will make you look very young. Your hair will not be white. Your skin will not have wrinkles. So this is again big market for that. And antibiotic resistant drugs. And this that these antibiotics will not get the virus to be resistant to your antibiotics. And wellness. This is all the various supplements which you all vitamins to help you to prevent certain diseases. So again, these are all the possible big markets. If you can come up with such drugs, that's why drug companies are interested to develop such drugs. It's always there. Of course, now with the COVID-19, that's also good for you can come up with such a vaccine, for example. This is coming from a company of Bauer and Company. Let's look at the return on investment. If I were to develop fertilizers to help the farmers, now what does it cost? So these are the common fertilizers: ammonium sulfate, triple superphosphate urea, and hydrous ammonia. This comes up to be about $0.21 US per kilogram. Now, if you look at the local vegetables, if you were to buy tomatoes at that point in time, 2008 and 2006, it's about 95 US cents per kilogram. And of course, red chili is more expensive, and also the green capsicum, the large chili, green color. But look at all the common medication. Muscle relaxant makes it relaxes the muscles. It's 5,800 USD per kilogram. Then you look at the paracetamol, which is a Panadol, 9,500 USD per kilogram. And it goes on. Viagra, hypertension, right? Hypertension, antidepressant, Prozac, and also the strong pain reliever, nearly $500,000 USD per kilogram. So if you have money, you want to invest, right? So the business people will say, I want to invest in generating new drugs to help cure the disease, make the world a better place, rather than investing in growing vegetables, tomatoes, chili, or even investing to produce fertilizer. So that's why the motivation is there to do this. And to do this, to discover new drugs, you need search. That's where the motivation is there. Okay. So I think almost time's up. So that's nice. So what have we learned today? We have looked at the heuristic search. This is a better search a more powerful search than your classical simple search, like the breadth-first and your depth-first, and even your bi-directional search. And we look at the definitions. How do we define? I think there's some comments there. Yeah, correct. And also at the same time, remember I gave you the survey before at the start of this lecture. If you want to make the world a better place, it's also a good choice. Of course, there's also, if you want to get rich, you can also learn about AI to actually predict when to buy, what stocks to buy, right? To help you become rich. Okay, so and the motivation for the heuristic search. And we spend some time looking at the simple previous search heuristic on the searching your way, finding your way home after a holiday in a country called Romania, to go from Iraq to Bucharest. This one, huh? And then we also, as a result of that, we see some of the limitations of the best first search, and we say that okay. Then we look at the better version, which is your A-star, which is the A-star search. And then in the last couple of slides, we look at two examples of why there is interest in AI and also in the search in terms of games development, right? So of course, these are the simple games that we did show to you, which is your Tello. And I think I'm quite sure many of the games you play, either online or the offline, actually has at the back there's some AI engine that is just for the to counteract your answer. You as a human playing with a machine, so the machine normally can be quite smart. Again, it depends on your what they call the level, right? You have a different level. If you want to have play against a super expert machine version, and so you can I think set a different level. Simpler levels, of course, the search will not be so complex, so will not will not always beat you. So if you think that you have reached a higher level, of course, that AI will try to be smarter than you. And lastly, we show you from the commercial perspective, from the business perspective, right? Drug design using search is also very popular and also interesting area for industry to focus on. Of course, I think also have other areas. Of course, this is only two of the not so mainstream, not so common things you may not know that AI has been used a lot. Okay, so that's it. So we'll stop here for today.
Okay, I think I understand this far.
Okay, let me stop the recording first. Okay. Okay. So I stopped the recording. Any questions, comments so far? So hopefully I've shown to you that why search is so important. It's not only just to search as in Google or even to search as in finding using your ways to search. Of course, ways is that. Of course, this is something that of course ways will be something that you can't take 1 hour to find the path, isn't it, from point A to point B. So it's been done within a split second, right? And of course, in the case of ways, I think there will also be some live information, like say a traffic jam along certain jalan. It's a roadblock there, police roadblock. So therefore, you cannot use that way. Okay, so if there's nothing else, we stop here. So I'll still here for a while. Otherwise, you all can go off. And I'll compile the questionnaire. Let me look at the questionnaire first. I think there's 58%, 57% saying that they want to continue the tutorial on the 20th of July. But unfortunately, there's a 14% of you said the RE students want to join back on the 22nd of July. So if there are some students who want to join, I think there's something on. So I cannot force them to have a class on 20th July. So probably RE4, you will be asked to join the Thursday morning tutorial on the 22nd. Now for RMH, 24% said they will join the following week's tutorial at 12:30. And there's a small number I think so small that I can't even see it. That join to tutorial on the 22nd July. So I think I put it this way. If the RMA students want to join on the 22nd, RE students, you are allowed to join, but please at the start of the class tell me so I can mark you present for the replacement class. Because I need to officially request for replacement class. Otherwise, when you check and say that I've not done my job. Okay. So looks like the class on the 22nd holiday will not proceed. It will be a holiday for you, right? So you have to replace it on other days, right? Okay, so I think I'll stop here. Go and have a lunch, and then I'll stay here for a while in case you have any questions. Thank you.
Thank you, sir.